I wanted to collect some observations from the example that we just did. So first of all, and this applies generally, separation of variables works for homogeneous PDEs and for homogeneous boundary conditions. And we'll talk later about what to do for non-homogeneous situations. It's also the case that it's the boundary value problem that determines the spectrum. So this is the sequence of lambdas that you end up using. And in particular for the Dirichlet boundary conditions, we see that this rolls over onto being Dirichlet boundary conditions for the the spatial ODE, and that ends up giving us solutions that look like sine. Actually, here, let me back up a little bit. Sine x root lambdas, and that leads us to the particular spectrum n pi over L quantity squared, and the corresponding eigenfunctions n pi x over L. And as a consequence, we are led, when we go back to looking at the initial condition, we need to find the Fourier sine series for the initial condition, because it's sine functions that we have to build with, to work with. There's another thing that's sort of nifty about this solution here, is that there's actually a Green's function lurking around. It's just not immediately visible the way we wrote it before, but we can rewrite this. So if we take uxt to be, let's see, so what was it? It was the sum n equals 1 to infinity of, and then we had some coefficient, and our coefficient was found as 2 over L integral from 0 to L f of xc sine n pi c over L dxc. So that's our nth Fourier sine series coefficient, and then we had the e to the minus lambda kt, and then we had the sine of n pi x over L. All right, now I can interchange the integral and the summation sign, pulling the integral out in front. So this is 0 to L, and then we'll have 2 over L times the series e to the minus n pi over L squared kt, sine of n pi xc over L times sine of n pi x over L. And this whole big mess is being integrated against f of xc with respect to dxc. And so if we identify this entire block in parentheses right here as g of xct, then we can rewrite this as the integral 0 to L gxc t f of xc dxc. So that is our Green's function. All right, and let's see. So we can actually take a look at what this what this looks like. It converges to a sort of line of Dirac masses down the diagonal of the square of side length L. And that's a pretty crap description. So let me draw some pictures. So this is some pictures as t goes to 0 of so here, yeah, let me write that down. So as t tends to 0, this is a picture of what G looks like. So here we see the progression as t gets closer and closer to 0. And in the end here, you can see this ridge forming right along the diagonal. So that spike actually tends up toward infinity. So it's like all along the diagonal here. So this is the interval from 0 to L in X and 0 to L in C. And all along the diagonal right here, we have these little Dirac deltas taking shape. Okay. Other observations. Well, let's look at what's going on at 0, 0. So U0t is supposed to be equal to 0 according to our boundary condition. But it's sort of in conflict with our initial condition of 100. So if we look at U00, 0, what do we get? Is it 0 or is it 100? Well, the answer is actually we don't care. And the reason why we don't care is because we're working in L2. And L2 is actually, it doesn't care about the value of a function at a particular point. So let me explain why. It's because we're dealing with integrals, right? And so if you have some domain like this, and you're integrating, and you've got some function that you're integrating and it's giving you this area, blah, blah, blah. And you take another function and you change the value of that function at some particular point, and you say, at that point it's now equal to this. And you know what? At this point here, I'm going to change it to be equal to this. The value of the integral doesn't change. Integrals don't care about individual points. In fact, integrals don't care about countable sets of points. So I could change the value, for instance, at all rational numbers. It wouldn't change the value of the integral. In fact, there's even uncountable sets of points that you can change it on without messing up the value of the integral. And now we just opened up like a whole hornet's nest of what's really going on here. That's a topic for Math 550 where we discuss measure theory. So for us, don't worry about it. But just notice that, hey, if your function's supposed to have value 100 at the corner and also have value 0 at the corner simultaneously, don't lose sleep about it. That's an okay thing to happen in L2. Secretly, we do a mathematical fudging, and we say L2 actually consists of equivalence classes of functions, where two functions are equivalent if they only differ by, say, finitely many points or countably many points, etc. Okay, so there's that. There's also another interesting observation, so leaving that last one aside, and that is as soon as t gets off the mark, so as soon as time starts progressing, if you look at the amplitude of these sine factors that we're adding in, they go to 0 really fast, right? Because each of them has an amplitude that looks like this exponential, and this exponential has, an n squared term in it. So succeeding terms of the sequence are going to be driven to 0 really, really fast. So these are very close to 0 as n increases. And so as a consequence, what that means is that your entire solution, so that entire infinite sum, it actually looks very, very much like just the first term after a very short amount of time. So if you're an engineer and you're doing a first order calculation or approximation on the back of an envelope, that's really all that you're sort of seeing. And if you remember the plot that I threw out there before, let me just bring it back. What you see is after a very short amount of time, this basically just looks like a sine curve that's going back and forth here. And that's exactly why. So all of the fine detail, and this also means that if you only take like the first 50 terms and you have some little Gibbsy jumping around here, like if you look closely, you can see I approximated, and it's actually not exactly the constant line 100. It's some approximation of it, so it's got some little wiggles into it. Those little wiggles, any fine detail is washed away almost immediately, and the whole thing becomes just a sine curve.